Today, we're going to pull back the curtain on your body's hidden emergency controls. We're talking about these tiny little switches that can literally mean the difference between life and death. Okay, think about this for a second. Have you ever been startled by a loud noise, like out of nowhere? Or maybe you felt that insane rush of adrenaline right before a big speech. You know exactly what I'm talking about, right? That sudden, full-body jolt where everything just goes on high alert. Well, that crazy physical reaction, it actually has a name, and I'm sure you've heard it a million times: the fight or flight response. It's this ancient, totally hardwired system that's all about one thing: survival. So who's in charge of all this? The master controller behind this whole alarm system is what we call the sympathetic nervous system. The best way to think about it is like a command center that just flips this giant master switch from, chill and digest mode straight to go time right now. But wait, how does that command center actually get its orders out to the troops? Well, it relies on two kinds of super important managers that are sitting right there on your cells. And that's what we're here to talk about. These are the alpha and beta receptors. So let's give these managers some simple job titles. First up, you've got the alpha receptors. Think of these guys as the squeezers. Their whole job is to tighten everything down and redirect resources where they're needed most. Then you have the beta receptors. These are the boosters. Their job is to ramp things up, accelerate functions, and open things up. All right, let's start with the first group, the squeezers, the alpha receptors. Now, if you remember absolutely nothing else from this section, just remember this one little phrase. A is for arteries. Seriously, this simple mnemonic perfectly nails their number one job. So how does this actually work? Well, you've got two main types. Alpha-1 receptors are sitting right on your blood vessels. When they get the signal, they cause what's called vasoconstriction. They literally squeeze your arteries. What does that do? It jacks up your blood pressure and shoves blood to where you need it most, like your muscles and brain. But then you have alpha-2. Think of alpha-2 as the brake pedal. It's located in your central nervous system, and its whole job is to basically say, whoa, okay, that's enough, and it dials back the alarm so things don't get completely out of control.
Okay, so that's Team Alpha. Now let's meet the other side of this dynamic duo, the beta receptors, aka the boosters.
And hey, just like with alpha, we've got a fantastic mnemonic for beta. If A is for arteries, then B is for beats and breaths. This right here is your key to unlocking the whole beta system. Okay, check this out. It's actually pretty easy to remember. You've got one heart, right? So beta-1 receptors are mainly in the heart. When they get activated, they boost your heart rate and make it pump way harder. That's your beats. Now you have two lungs. So beta-2 receptors are mostly in the lungs, and their job is to open up your airways so you can suck in more air. That's the breaths. See? One heart, two lungs. Oh, and there's also a beta-3, which is found in your fat tissue. It helps break down fat to give you a quick burst of energy. So, there you have it, the squeezers and the boosters. This is all really cool biology for sure, but why does it matter in the real world? Well, here's the kicker. Because we understand this system so well, medicine has actually developed a whole set of master keys to control it. So let's put it all together. You can see the alpha and beta columns right here with their different subtypes and what they do. But I want you to look at the bottom two rows, agonists, antagonists. These are the drugs we were talking about, the master keys that can either turn these receptors on or turn them off. So for example, a drug like phenylephrine can flick the switch on for alpha-1 receptors, while something like metoprolol can go in and block the beta-1 receptors. Let's make sure we're totally clear on this. An agonist. Think of this as a drug that acts like a perfect copy of your body's own key. It slides into the lock, the receptor, and turns it, activating it. Now an antagonist, which you'll often hear called a blocker, is kind of the opposite. It's like a key that fits perfectly into the lock, but instead of turning it, it just gets stuck and jams it, so nothing else can get in to turn it on. Okay, let's see how this plays out in the real world. Let's say a patient has high blood pressure, and it's because their heart is just working way too hard. The root of the problem? Those beta-1 receptors in the heart are getting overstimulated. So what does a doctor do? They prescribe a beta blocker, an antagonist, like metoprolol. So this drug goes straight to the heart and does what? It jams those beta-1 receptors. And the result? The heart can't get that go-go-go signal anymore. The heart rate slows down, the pressure eases up, and blood pressure drops. It's simple, it's elegant, and it's absolutely life-saving. So you see, this is so much more than just memorizing biology terms. By knowing exactly what alpha 1 does, what beta 1 does, what beta 2 does, medicine can create these incredibly precise drugs that go in and flip just one specific switch while leaving all the others alone. It's almost like having a remote control for your own body.
And that really leaves us with a pretty mind-blowing question for the future, doesn't it? I mean, we've gotten so good at controlling the heart and the lungs with this incredible precision. So, as our understanding of all these little cellular switches gets even deeper, what else could we fine-tune? What other fundamental systems of the human body might we be able to safely and effectively adjust next?